Okay, so this is part 6. We're going to talk about propagation and how the nervous system can differentiate between stubbing your toe and getting your toe cut off. So this is just propagation of an action potential. So really, I'm going to try and draw this just so you can see how it's constructed. So basically what we have are patches that are going to happen. So here's the point of stimulus. So this patch, instead of being positive on the outside, negative on the inside, that's going to depolarize. Right? Acetylcholine binding to chemical gates at the motor end plate causes this to happen. So then these guys are at rest, but what's going to happen is that these guys will then go through depolarization. And it causes this patch to depolarize, and it causes this patch to depolarize, so on and so forth. So this is just showing how depolarization is happening here. It'll then cause depolarization here, depolarization here, depolarization here. So it's kind of like a cheesy wave at a sports stadium. So that depolarization wave is going to travel all along these channel proteins, all along that membrane, be it the sarcolemma or the axonema. So I wouldn't worry too much about what is written here. That's really the take-home message, right? So here it is, and then it's moved, and I'm just gonna, and it's moved again. All right. As long as you understand that propagation part, that is the take-home message, and that's why that end plate potential. Let me back it up here. Whoops. That end plate potential, right? We have chemical gates right here. And their job is just to get this patch to depolarize, which will then initiate an action potential that will then propagate all along the sarcolemma, right? And that's also why we have graded potentials. If it's strong enough, it'll kickstart an action potential. Okay, so the threshold, we said it's depolarized to 15 by 15 or 20, so we're talking about 50 or 55. A strong stimulus will cause an action potential, a weak one will not. And action potentials either happen completely or not at all. An action potential is going to look like that, or it doesn't happen, right? If the stimulus is weak, then it goes right back down to that resting membrane potential. And as we said, all action potentials are alike, regardless of the stimulus intensity. So what happens is the CNS, your brain, determines stimulus intensity by the frequency of action potentials, right? So here is stubbing your toe, and here is cutting your toe off. So your central nervous system is seeing more action potentials in a shorter period of time. And so strong stimulus is going to generate action potentials more often, and we have to talk about now how and why. So we have what's called an absolute refractory period. An absolute refractory period basically means that another action potential cannot happen. And that absolute refractory period is when we're having an action potential. We can't have another action potential when we're in the middle of an action potential. Okay? I think, yes. So here, okay, this area right here, this is our absolute refractory period. No matter if you cut your whole friggin' leg off, you're not going to be able to generate another action potential because you're already in the middle of one. But what we have here is this relative refractory period, which is during this hyperpolarization. And this is on the slide ahead, but I might as well talk about it now. See, a stronger stimulus will be able to generate another action potential right here, even though we're further away from that threshold. A weaker one, it's still strong enough to generate an action potential, but it's going to have to wait for those sodium-potassium gates to get it back to minus 70. Then it can generate another action potential, whereas if the stimulus is strong enough, it's going to generate one right here. So your central nervous system is seeing a difference in the frequency of action potentials. Okay, So this relative refractory period is during hyperpolarization. Okay, and that is the end of this section.